Hi, good afternoon, everyone. Welcome to this wild webinar this afternoon. I hope everyone is doing well. This is the last webinar in our electronics. So Sam and I will be talking about reliability physics this afternoon. If that wasn't what you're expecting, then you're probably in the wrong place. If that was what you're expecting, then nice to see you this afternoon. Just some housekeeping to get us started. Everyone is on mute, so I hope that's what you're expecting. If you've got any questions or comments, please just pop them in the chat. We are able to see those and we will answer them during the Q&A at the end. If you have any queries which we can't answer live just because they're a bit too in-depth or whatever, then we do have your email addresses, so we'll come back to you at the end and we'll reach out to you afterwards. And as I just mentioned, this is the final webinar in the series. So if you want to go back and watch any of the previous webinars, they are all available on our website, so you can just go ahead and watch those on demand when you are ready to. So in terms of why we're all here, why is electronics reliability important for small to medium-sized businesses? Obviously, at this point in time, electronic systems are found in near enough all industries, aerospace, automotive, consumer electronics and products, healthcare, industrial, pretty much everything. So ensuring these systems remain operational and perform to their intended function in a variety of environments is critical to product success and customer satisfaction. Companies who properly address electronics reliability concerns, particularly through simulation, can meet many of the objectives that you can see here mentioned. Typically, companies have used a design, build, test, break, fix design cycle. However, this approach can be pretty expensive and time-consuming. Design rules and best practices may not provide engineers with enough guidance to properly design modern cutting-edge products. By using simulation, virtual models and prototypes can be created and simulated, which provide engineers with a much higher degree of confidence that the physical tests you do run are going to be successful. Looking at performance, safety, and cost are all critical considerations in the design of electronic systems. Devices are required to reliably perform in their intended function in a wide variety of demanding environments. If systems get too hot, if they have a mechanical failure, if they're not able to perform to their intended function, this is obviously a bit of a problem, especially in some instances, this could put people at risk. A wide variety of customers have already benefited from Ansys electronic reliability solutions. Benefits typically include reduced design and development time, material costs, including fewer board redesigns, reduced product development timelines, and all of the benefits you can see mentioned here. We have a number of assets we can share with you if you'd like more detail on the benefits mentioned here. Engineers obviously need to address a wide variety of design requirements when designing electronic systems. These range from electrical, such as signal power integrity, thermal, such as the implementation of optimal cooling strategies, or mechanical, the ability to withstand thermal cycling, shock, vibration, drop. Further, products are expected to meet life requirements to ensure they meet their intended function for at least a specified amount of time. Engineers also need to consider the effects of manufacturing, transportation, product operation as part of their design process. Ansys do provide a suite of tools and workflow solutions that address a wide range of electronics reliability concerns. As I mentioned, we have covered the first 4 topics mentioned here previously, and then today we're going to look at reliability physics analysis specifically, to look at how these play a key role in the understanding of how electronic systems operate and perform in a variety of applications. Having a good understanding of electronic systems, electrical, thermal, and mechanical performance under various conditions is really important. However, reliability physics analysis tells us how long a product is expected to last under such conditions. Tools like Sherlock can be used to determine the time to failure or cycles to failure for all of the components on a PCB using various inbuilt reliability models. This is where my wonderful colleague Sam comes in, who is going to be able to talk you through all of the wonderful ways in which that can be done. So over to you, Sam.
Okay, hi everyone. Thanks, Laura. So I'm Sam, and today I'll be giving you a short look into Ansys Sherlock, which is Ansys's reliability tool, which focuses on the reliability of printed circuit boards. Traditionally, now we've already kind of gone through this slide, but I'll go through it again. So traditionally, the PCB printed circuit board design process follows a design, build, test, break workflow. and built a physical testing using this process is expensive and it can be time consuming. So yeah, a little stat there. So 73% of the product development costs are spent on this cycle. Ansys Sherlock can be used to reduce the number of design iterations associated with the cycle and reduce costs involved in this process. So the goal of Ansys Sherlock will be to take as many of those design cycles out of physical testing and into simulation. The results you obtain through Ansys Sherlock can give you confidence that your products will meet your desired reliability goals. Okay, so what is Ansys Sherlock? So Ansys Sherlock addresses the question of printed circuit board reliability. By identifying issues through simulation before physical prototyping takes place, we can significantly reduce the number of cycles in the design process. Ansys Sherlock uses various physics to predict life cycle reliability for your PCB. So that includes thermal cycle fatigue, vibration, and mechanical shock to analyze components, boards, and connections. Ansys Sherlock offers analysis for all engineers. So other assessment tools, other typical FEA assessment tools typically require a specialist in that particular area to carry out the analysis. But Sherlock provides a pre-packaged, ready-to-go approach, which is friendly for PCB designers. On top of that, Sherlock synergizes well with other Ansys products, so you can see that list there. As an example, Discovery, Icepak, and Mechanical. So models from Sherlock can be exported into these other Ansys software packages, where you can have a slightly deeper dive with greater fidelity into the issues you're facing. Okay, so reliability concerns need to be addressed at different stages in the design process, and that design process is what you can see roughly outlined here. Costs associated with fixing reliability-related issues also increase as designs mature. So as products get towards the end of the life cycle, that's when you start to see the majority of costs incurring. Ansys Sherlock can be used to address issues at various stages in this design process. So those stages which are highlighted in yellow there. For example, initial part selection and initial part placement. So Sherlock has a vast library of parts to choose from that can be dropped very simply into your analysis. Following that, parts and the placement of parts can be easily changed and refined to achieve your final layout. And then finally, design for manufacturing. So Sherlock allows optimization to easily take place to get you to that point. Okay, so before we carry on with the slides, I think this is a reasonable point to show you a quick demo, just to give you a quick indication of what Sherlock looks like and how it functions. Okay, so if you just bear with me 1 second, so you should all be able to see Sherlock on your screen now. Okay, so when we open Sherlock, this is what it looks like. Now this isn't like a technical training session, although I will try and explain things where I think necessary. But the key thing on this left-hand side here, this is where our projects are stored, and everything related to a particular project will be found under here. So for example, we define our inputs, we'll view our results, all under this tree, as you can see here. Now, a Sherlock project typically starts by importing a PCB file. And now you can see here that Ansys Sherlock does deal with a number of the common PCB file types. So that's one of those here. Now, this analysis that I'm working with at the minute, it's kind of a ready, steady cook, ready to go approach. So I've completed the analysis and everything's solved, just so we're not waiting for things to solve within the demo. But that's typically how you would start a project, by importing a file. just to show you what we're working with, I will, bear with me 1 second. I will just load up a picture of the PCB here. It's on the screen, so I just need to move it across. So this is an idea of what we're working with. And if I show one of the copper layers, yeah, so we can see here that I've imported this PCB successfully, and that's what it looks like. Once the PCB's been imported, I can define the various inputs that are required to for my reliability assessment. So for example, if I double click on Lifecycle, here we can define the reliability goals relating to this particular PCB. So we can see here that our target for this PCB is to have at most 20% probability of failure after a service life of 5 years. Under this heading here, this is where we define the loads which our PCB will face during its life cycle. So you can see there are some that are predefined here, one for an environmental condition when the PCB is in use, and also one where the PCB is in transit. So if I right click on here, we can see that there are 4 different types of environmental loading that Sherlock can handle. So thermal cycle, harmonic vibration, random vibration, and then mechanical shock as well. So those are the 4 main categories that Sherlock has to offer. If I just look in detail at one of these and open up the temperature cycle, you can see here that a thermal profile, a simple thermal profile, has been defined, and also the number of times that cycle will occur during its life cycle as well has been defined. Same sort of thing, but for a mechanical shock event here. So something to do with getting hit by a shopping cart is defined within this load cycle. Okay, so those are the types of load that will be defined. And now what exactly is it that we want to get out of Ansys Sherlock? So if I just skip quickly and over to our results, if I just click one of these here. So if I look at the scorecard here at the top, what you can see is the different types of analysis that Sherlock has performed. So we have one relating to a harmonic vibration, one relating to ICT analysis, one relating to mechanical shock. And what Sherlock does is it gives each individual component a score out of 10 based on how well it's performing related to our reliability goals. So we can see that harmonic vibration, which is at the top, we've had 92 components, which is just over 40% of our components, scoring a 7 or more, which is good, which basically means that it's met our reliability goals. If a component has scored 3 to 7, that means that it's not quite met the reliability goals, and it could do with some improvement. And if it's less than 3, this means that yeah, it's way below the reliability goals and it needs serious improvement. So this scorecard here is a way of quickly seeing which analysis types cause our PCB to fail, if any, and then also how many of the components that make up our PCB are problematic. Okay, so that's the scorecard. That's just a quick way of seeing which analysis types and how many components are an issue. If I move on now to life prediction, which is another one of the headings on the left-hand side here, what this view gives us is the probability of failure for each analysis type as the lifetime of the PCB progresses. So you can see here, the straight line is just our reliability metric, so aiming to meet that a probability of failure of less than 20% over 5 years. And it just gives us a nice overview to see which analysis types are not meeting that goal. So you can see there's a number of analysis types here which are beyond our goal. Now, if I just look at the analysis type which was the most problematic, which was the harmonic vibration one. If I have a look at this screen here, the one that I've opened, this screen gives you a much more detailed view of which components are a problem. So again, each of these components is given a score, which you can see on this right-hand side. And each row in this table is an individual component. So at the top of the table, you'll see the components that are performing the worst. And if we scroll down, there should be some at least, yeah, you can see here that are performing a bit better. But this view just gives you like a more detailed view into the score of each individual component. Similarly, we can look at the life prediction again, which is just the same thing we saw earlier, but individually for that analysis type. So because your PCB is only as good as the worst performing component, that worst performing component is the only one that's displayed here. Okay, if I wanted to view that life for any particular component that isn't the worst case one, it's as simple as just right clicking it and then view life prediction, and then we can see the corresponding graph for that component there. Okay, so that was just harmonic vibration that I was looking at there, but the same sort of thing can be done for the other analysis types. So for mechanical shock, if we open up the table relating to mechanical shock, we can see the exact same thing here, highlighting all the components which are a problem. Now, this way of doing things is kind of cumbersome and it's not very intuitive to read off your problematic component from a table and then go in to find the component. So one thing you can do is if we go back to our PCB view, which is just loading if you give it a second. Okay, now I'm just going to hide a few components from this. Okay, so within this view, we can actually see our results presented in the form of a plot. So again, if I go back to our worst performing analysis type, which was harmonic vibration, I believe. Yes, it was. So if I view the results here, so these are the same scores that we saw a second ago in tabular form, except it's presented in a nice way where we can see it on each component. So anything indicated in red is that low score of 3 or below. Anything in yellow is a middle score of around 3 to 7. And then anything in green is a high score, which means it's passed our reliability metrics. So you can see there that you can either plot the score for each component. So you can plot the score for the components on the top. You can plot the score for the components on the bottom. Or what you can do is you can look at the stress and strain results, which led to that particular score. So, for example, for harmonic vibration, we can display this view, which gives us the displacements relating to our harmonic vibration. Similarly, we can look at stress and strain plots. So, for example, strain on the top and stress on the top. So you can see here that the fixing points for our PCB are the most highly stressed areas, with a little bit of region in the middle which is stressed also. Again, you can do the same sort of thing for each analysis type. So for mechanical shock, if you want to do the same thing, it's really easy to highlight which components are problematic. Okay, so Now that's done, we've performed our Sherlock analysis, and let's say we've got these components here, which are an issue. It's dead easy to switch out these components with a different component and then re-simulate the analysis and then see if it passes. So that's done very easily if we click edit and then choose the type of thing that we want to edit. So for example, if I go to edit components, and let me just hide some of these so I can see that. Okay, so let's say I believe it was this component here that's failed. All I need to do is, well, first of all, I can right click it. I can either move the part or change its orientation, or I can edit the part, which will allow me to, 1 second. Yeah, so that allows me to switch out that component for a different component, which might be better performing. I can change other things relating to that component. So for example, the solder material, we can change, or we can change, let's see here. Yeah, we can basically change any properties relating to that particular component or switch it out for a different one. Once I'm done changing that part, all I need to do is click close at the bottom here, and then the PCB will be updated. Again, just to show you something else, if I wanted to say, for example, edit our mounting points, again, dead simple to do. If I wanted to add another mount point, for example, just to say to see how our analysis results change, all I need to do is right click and then add a mount point, and then we can see it. All we need to do is fill in our fields here, which define our mount point. Just hit save, and you can see that a mount point has been added there. So in that sense, Sherlock makes it really easy for PCB designers to quickly make changes and then resolve and see the results. So performing these types of changes with physical testing, again, it would be time consuming and it'd be expensive, and moving that into simulation will ideally save a lot of time and money. Okay, so there's a fairly quick demo into Sherlock there, and we're going to continue with the slides now. Okay, so Ansys Sherlock features an extensive library of materials, but how does this work? Well, when we import a file type which contains our PCB information, such as part size, package type or name, it doesn't contain all of the information we require for analysis. And again, that's something that's usually done by an analysis, so geometry preparation and meshing and model setup. So that's something that's usually done by an analyst. But Sherlock uses its database to automatically fill in everything you need for your analysis. So this makes part selection and change management easy. And with the latest software release, the Sherlock parts library has increased from 250,000 to over 600,000 parts. Okay, so in the past, FEA-based reliability assessments were only performed by simulation experts. So this tends to lead to delays because the PCB designer has to kind of outsource any thermal simulation to a thermal engineer, mechanical simulation to a mechanical engineer, and so on. If these analysis find any reliability issues too late in the design process, again, the costs associated with that will be quite high. The solution in this case, and what Ansys Sherlock offers, is to take the analysis into the hands of the PCB designer. And Ansys Sherlock allows the PCB designer to perform the mechanical, thermal, and electrical simulations, which the analysis would usually be taken care of. Okay, so we kind of went through this in the demo. I'll go through it here in this slide again. So this kind of just shows you the typical workflow of Ansys Sherlock. So first, we'll upload our ECAD design, which contains the most of the information relating to our PCB. We'll then apply the loads that define define the load and input for the PCB's life cycle, and then we'll find the failed components, and then we'll redesign and repeat this process. Okay, again, we went through some of this in the demo, but this slide just goes through the various analysis types available in Sherlock that you can see on that left-hand side there. In the middle is where we've defined our life cycle inputs. So again, mechanical shock, random vibration, thermal events, that sort of thing. And then on the right-hand side is some of the post-processing we can do. So we've not shown that in the demo, but you can post-process in 3D, like you see in there. Again, another thing we went through in the demo, but reliability physics analysis via Ansys Sherlock. It provides time to failure predictions for every component based on physics of failure techniques. And it displays these in intuitive tables, graphs, and plots. So Ansys Sherlock allows you to quickly make design decisions to assess the relative impacts on reliability. So this slide is just going through some of the changes which you might make, which you could make within Ansys Sherlock very quickly. So for example, can you change the pad size? Can you switch out the package to a different package? Or perhaps change the laminate to different material properties, different thickness, etc. Okay, so the final slide here on my end is just to run over the benefits of Sherlock. So it helps avoid redesign and retest due to failures during constant temperature, thermal cycling, power cycling, vibration, and mechanical shock. It helps to eliminate manufacturing defects and communicates quality and reliability throughout the electronics supply chain. It increases first pass yields during manufacturing, helps reduce warranty returns in the field. The board life level predictions help to assess risks associated with shock, vibration, thermal cycling, and other conditions. And it introduces best-in-class modeling techniques that can be used to perform more advanced thermal and mechanical reliability studies in Ansys Mechanical, LS Dyna, and Icepak.
Thanks, Sam.
Okay.
So just a quick reminder to everyone before we go on to the Q&A. We do have our technology showcase coming up on the 15th of November, so just a couple of weeks now until that is coming up. If you would like to register, I've popped the hyperlink there for everyone. It is on our website. It's free to go along, but we do need to have everyone registered just so that we can control the number of places. So there's going to be quite a lot on show there to do with our PTC arm of our business, the Ansys arm, lots of networking. So if you'd like to come along, please do. If you want any more information, please let me know in the chat, and I'm more than happy to reach out with that. Otherwise, if you've got any questions, please do pop them in the chat and we will be happy to answer those for you. I appreciate we've only got a couple of ticks left. If you've got any Q&A, please pop them in the chat for us. Otherwise, feel free to email us on info@wildanalysis.co.uk after the webinar. If you're anything like me, you'll think about the question about 3 hours after this webinar is finished. So I'll just give everyone a couple of moments to pop that in the chat if you have got any questions for Sam or I. I can see someone's mentioned, Sam, you mentioned that Sherlock allows PCB designers to perform assessments usually performed by simulation experts. What makes Sherlock different to allow this?
Yeah, sure. So it's a good question. So the typical FEA process requires someone who's experienced in FEA to prepare the geometry, mesh that geometry, and then finally set up the model, so defining any connections and boundary conditions. But the advantage of Sherlock is that kind of process, so the geometry prep, the meshing, and then some of the model setup is covered by the Sherlock database. So for all of the components which are within the Ansys Sherlock database, all of that information is kind of pre-packaged and ready to go. So when you import it into your PCB, into your Sherlock analysis, it will be meshed, and it'll have the connections defined already ready to go. So it takes kind of most of the work out of it there. There is still like the need for an analysis. So if you wanted to do that kind of like higher fidelity level of analysis, as you can see, that as stated a little bit ago, so Sherlock can export its models out to software in the Ansys suite of programs, but in terms of getting designs out quickly and efficiently, Sherlock's great at that.
Brilliant. Thanks very much, Sam. I haven't got any other questions just at the moment, so I'll give everyone just another minute in case anyone wants to type anything. Otherwise, that will be the end of the webinar for today. I hope everyone has a wonderful afternoon, and we look forward to seeing everyone on the 15th of November for our showcase event. Yeah, I'm not seeing any more questions coming through, so thanks everyone for attending, and we will see you on the 15th.